Okay, so lecture today. So last lecture, the topic was like the pure relational algebra and tuple calculus, which were uh, which are kind of formal animals under kind of standard set semantics. But they're not really that practical. So if you recall that there was a picture before, like kind of the idealized picture, this is a more realistic picture of what actually happens in database systems. One sec. I want to make sure that the chat is up because it disappears when I go to share screen. Okay. So the realistic picture, and this is essentially what happens in all your modern relational database engines. What happens is the language is not tuple calculus, but rather SQL, which I'm sure you've heard of. And these get translated into what's called extended relational algebra. And that is the relational algebra that we dealt with last lecture, but it has a fair number of extensions to it to make it more practical and make it handle, just gives it more power. So the extended relational algebra is, strictly speaking, much more powerful than the standard kind of logical relational algebra. Now, what happens inside the database system, and we won't really cover this in this course, but if you're interested, you can take the advanced database course, which I teach, which is 5D187, which has a lower number than this one, which is 5D202, but that's just a quirk. But in that course, we actually go into the actual real nitty-gritty of how this optimization process works. But the point is that when you map to relational algebra, not all relational algebra will evaluate at the same speed. So what you can do is you can find equivalent relational algebra expressions which execute much quicker. All right, so that's kind of the task of the modern database engine, is to do that query optimization. All right, so the first thing that we want to mention is that the extended relational algebra is not based on a set semantics. It's based on a bag semantics. All right, and a bag allows for duplicates. So the more. One second, let me close this door here. So the more mathematical notion of that is called a multiset, but we'll call it a bag. Mathematically, actually, multisets are really difficult to kind of do proofs over, and to really get good mathematics developed for kind of formal mathematics developed for multisets is difficult, although it's an active research topic. So there are actually several like open problems that people are interested in. If anybody who considers himself to be like some kind of mathematical genius, I can, and I won't trouble the class with it, but I can present to you a couple problems and proofs that if you could actually show them, you would be you would make, you would be a big shot in theoretical computer science. So there are some database problems that have been open for like 40 years now, and I can state them pretty clearly, I think, and then it will be up to you to prove one way or another. But it will be, if you're a genius, if there's any geniuses in the audience, you might want to cut your teeth on this one. That would be quite a start to your career. Okay, but what I'm going to say is that bags are tough mathematically to kind of go with. So this is an example of a bag. You have duplicates. You have one big duplicate. That's also a bag, but it also happens to be a set as well. So when we talk about extended relational algebra and everything going forward in this class, we're always talking about a bag semantics rather than a set semantics. And why bags? Well, I mean, SQL is based on bags. It's a bag language. It's not a set. It doesn't have a set semantics. You can crunch things down to sets if you want, but it's bag. That's what it comes out of the. That's what it comes out of the box as a bag. Some operations like projection are more efficient on bags than sets because, we'll get to kind of what projection is over a bag in a second here. So here are the operations on bag. We have selection, so it applies to each tuple. So its effect on bag is like these are all very, this is all very simple. So let's just show it instead. Okay, so bag selection. So we have here, this is a relation under a bag semantics, because notice here the tuple 1, 2 is duplicated, right? So this selection here, now this could be something like A is less than 5. Let's consider that for a second. A is less than 5, and actually nothing, if I said A well, A is less than 5, both of these would be true. Now notice right here, this is kind of sneaking something else in here. We have A plus B is less than 5. So these arithmetic expressions here in the select, as the select condition, that actually is an extension over our, that's also a simple little extension. So we allow ourselves to kind of put in these arithmetic expressions into the conditions. So A plus, okay, so this is 3 less than 5. Well, is 11 less than 5? No. So this one does not qualify. But as it goes through, it just does it on a tuple by tuple basis. And of course, what it returns is a bag, right? So with the duplicate. So I hope that's clear what that's doing. Bag projection. If I project A over R, then it's going to just return back 1, 5, 1 here, because it's going to go through and it's going to allow for duplicates, right? Now, the reason why this is more efficient under bags is because all it has to do is run through these things and doesn't have to check to see if 1 is already there. All right. So if it was under set semantics, you'd have to check and see that 1 was duplicated. And well, we'll talk. I mean, that is more memory intensive. It maybe doesn't take that much more time, but it is memory intensive because you have to kind of keep a record of what you've seen already. Bag product is also very straightforward. It's just, you just kind of like, if you have n tuples and m tuples, you'll get n times m matches. It'll kind of just do the full product. So 1, 2, 3, 4 is being duplicated, of course, right? Okay, so that's the bag semantics under product. So bag theta join is what we show here. So we're going to show R bow tie, and then here's the theta join. Now notice what we've done here, because now we're stepping up to kind of a bit more, a little bit less mathematical, kind of more kind of broad use here. What we're allowing for here now is we're allowing for a little bit of syntactic sugar on the namings, so we don't have to do all those renamings. Like I was trying to force everything down to the kind of the core operations in pure relational algebra, but now let's just get a little bit. Let's just kind of be a little bit kind of not informal really, but let's allow for the assumption that we have some type of preprocessor that could resolve something like this. So when we're doing a theta join of R and S, because they do share B as an attribute, we're just going to assume that it gets aliased. So aliased, you'll see that there's aliases in SQL. What we're going to assume here is that to address this B here, you can say R dot B, and to address this B here, you can say S dot B. So what this does then is it basically will do that join. It'll do that theta join. Right? And the bag semantics just means that you allow for these duplicates to kind of go through. So I hope this is fairly clear what it's doing. Bag union, it will actually, well, I mean, it'll do kind of what you would think it would do. It will allow for the duplicate. So if you union 2 bags, you're just gonna, push them together, right? So that is union, and then intersection rather. It will basically do a matching. So this is intersection can be it's not complicated, but it's kind of more one of these things where the intersection means that does it takes like the like for 1 here, we have 3 1s here and we have 2 1s here. That means that 2 1s are going to survive the intersection, and of course 2 1s survive the intersection there. So it's just kind of a way that these things kind of get defined. I hope it's fairly clear. Right? Bag difference, likewise. I mean, if this 1 here will make that 1 drop out, this 2 will make that 2 drop out, and it'll leave this 1 and this 1 in the result. Okay, so bags are I think it's pretty straightforward. A bag is, but you just have to be aware that extended relational algebra and SQL are operating under a bag semantics. Okay. All right. So good. I got a question here. Okay, good reason for keeping duplicates in relations using bags is that it's easier to correctly calculate averages. think it might be true. Sustainability. I mean, if you mean sustainability in the environmental sense, I mean, I don't think the energy usage of having a bag semantic. I would say actually, bag semantics are better energy as far as energy goes. So because what bag semantics they allow for you to be more efficient with processing. Now, when you talk about bag semantics in terms of like the actual modeled reality, so databases are a little model of the world, and then you're I don't know. It's an interesting question though. How much does a bag semantics reflect in terms of like maybe excess inventory? I don't think it probably has much of a relation, but it's okay. I see that the question was what, but I mean it's an interesting question to come up with about how does the semantics impact things. I think there's probably a lot of people who don't really know what semantics they're using in the real world, but they are using bag semantics, but then they might get a little confused by that sometimes. I think that what happens sometimes with bag semantics is you have like, it can lead to some kind of subtle errors. Now, as far as keeping more hard drives and servers and all that, what was I gonna, that's not the issue. I think when it comes to sustainability, I don't think the issue is so much storage as it is performance, as it is to running CPU cycles. I think that's kind of how I would that's my judgment about, but I'm not an expert, so I don't know, but I'm just guessing that the more critical thing would be execution time. But it was a good question. Thanks. All right. So let's see here. So bag semantics is kind of it has some of the set laws. So our union S is S. So the commutativity of union. So that our union S and S union are the same thing. But that gets preserved in the set laws. But idempotency, meaning that S union S equals S, that does not get respected. So when you union things together under bag semantics, well, this is actually kind of complicated in SQL because SQL, when it does unions, it reverts back to set semantics. So it's a little quirk in SQL. Because otherwise it would lead to a lot of problems. Actually, it would lead to, I mean, just as a human factors, the issue would lead to a lot of problems. So SQL, I mean, a lot of mathematicians despise SQL, but they don't have anything better. I mean, it's well, I don't think that people are that interested in the whole kind of mathematicians versus the SQL practitioners debates. But the in a pure bag semantics, when you union something together, you duplicate it, right? But then, of course, the caveat is with SQL, if you union, you don't duplicate, which is just a quirk of SQL, and how SQL treats union operator. But that's something that to keep in mind is that these laws fail, and this is one of the reasons why it's so difficult to deal with bags under with mathematics. Anyways, I mean, it can be kind of somewhat interesting, at least from something like me. I'm actually interested in kind of the mathematical side of things as well. So, but maybe a little more interested in practicality these days. But I have a background in some of the math stuff. So okay, all right. So now we're going to get into some operations that are really this is our extended relational algebra. So now that we have bags, we're going to have. Let me just start out with this delta operator. Which basically eliminates duplicate from bags. So it turns bags into sets. Okay, and then we have another one which will sort tuples. All right. Now I was telling before, in the pure kind of mathematical sense, that when I have a relational algebra, set of operands which are relations, and I apply these operators to them, I always yield back a relation in the pure relational algebra. Well, when you start sorting things, and actually what you're not really returning back a relation anymore, you're returning back a sorted relation. Okay, so already this sorting operator is already kind of completely blowing away the whole algebraic status of what we're doing. All right, that is that things should stay closed under the operations. So sort, but let's be practical here. You want to sort tuples. I mean, if some mathematician that says, well, we don't want to deal with that because it's going to cause all our problems with our formalisms. The practical person is saying, yeah, but we got to get the database to do something in the world here, and we need to sort tuples, right? So we're gonna basically junk your whole kind of mathematical heaven for the practicality of something much more complicated but practical. All right, so sorting tuples is the tau operator, and then the gamma operator. And by the way, people, I mean, just to kind of throw, you know, you should know your Greek alphabet. I think probably a lot of you do, but you should know. I mean, you should know your Greek alphabet. I mean, go and look at the Greek fonts and just memorize out, the alpha, beta, gamma, tau, delta. I mean, lower and uppercase. It's a mark of education. Okay. And also it just helps kind of when you have to consume mathematical material. All right. So then we have the gamma operator, which is grouping and aggregation. All right. So that is really causes things to be difficult mathematically. And then we also have outer join, which we'll talk about, which has to do with a special way that we're going to. I mean, outer join is just it's going to be the bow tie with an O on it. That's what our outer join is. And then there's a little bit of extra syntax there too to do with left and right and full outer joins. But that's something that we're also going to cover. So these right here are the operators we're going to cover now. I'm going to go through these. These are the ones that are kind of going to spice up the kind of the base relational algebra, right? So the delta operator is trivial. It's just like you just apply it over a relation, and it will go through and remove extra copies, right? Return it to a set. So yeah, there we are. So if you do it, if you have that original relation, we have the 1, 2, this right here, and you do a delta operator over that relation, you're going to remove the duplicates. There they are. They're all gone. Okay. So sorting, what that's going to do is okay. So L here, tau sub L R2 is a list of some attributes of R2, the relation R2. So what it's going to do then is it's going to basically sort first on the value of the first attribute on L, and then on the second attribute, et cetera, et cetera. So it breaks ties arbitrarily. So it's under set semantics I'm sorry, under bag semantics. It doesn't have to do anything with bag semantics, actually. We'll scratch that me saying that. But basically, what this can do is this sorting operator, and this is true in SQL as well, it can introduce a little bit of indeterminacy in your answers. So in other words, you might have two relations, or you might have a relation that you're going to do a sort on, and you do the sort 1 second, and you get a particular result, and then you do the sort at another second, and you might get a different result. So that's what I would call indeterminacy. So what it might be just is that if it's breaking ties arbitrarily, it may just be some kind of strange artifact of the physical data structure or something that determines that one tuple goes before another. So something to keep your eye on. But I hope that the sorting is kind of clear. Let's see here. Okay, yeah. So the tau operator is the only operation whose result is neither a set nor a bag of tuples. It's a sorted set or sorted bag of tuples. So what we have here is we have if you say sort on B here, then it could basically result in here because we have a tie here on B 5 and 1, and so it puts 5 here first, and then it puts 1 here, right? So that's just showing that it's arbitrary because both of these have a tie. The first and the third tuple have a tie on B. Now, if you want to, here's a little trick for you, just to keep in mind for recitation. So the next recitation after the one, yes. So you can have a secondary attribute which breaks the ties, correct. However, even that can then result, if you have 3 attributes in the relation, even that can result in an issue where you're going to have to break the ties. If you say that, well, why don't we just sort on every attribute in the relation in some ordering, you can still have kind of some arbitrary aspect there because you have the bag semantics. So it's like you really can't make it determinate in a pure sense. But that's that has to do with well, there's a deeper issue there that I won't bring it up, but there are some deep issues about that. If people who want to kind of like look these things up, there's an issue of value orientation and object orientation that kind of is the relational model is value oriented as opposed to object oriented. That's kind of the old story on that. But anyways, there's the kind of a mathematical kind of way to kind of really kind of get to the heart of that, or to really kind of be precise about what I'm talking about in terms of this issue of indeterminacy and sorting. Okay. Now we get to the aggregate operators. So these ones are. This is where I think that these are the ones that are the most, I would say, tricky to understand. So let's go. Let's go through these ones. Um, let's go through this in a kind of a very plotting method of, kind of slow way. Aggregation operators are not operators in relational algebra, of course not. Rather, they apply to entire columns of a table that produces a single result. Okay, so the first thing to say is that what an aggregate operator does, what it takes as input is, you could say, like a bag of values, or you could say a vector of values, if you want to see it that way. But what it's taking in is it's taking in, or a sequence of values, if you want to call it that way. Let's say, let's call it a, oh, I don't want to get too confusing here. Let's call it a bag of values. Let's just call it, just to kind of stay kind of, it's just a bag. It's a bag of single values in the simple case here. So it's a bag of like atomic values. So it could be like a bag of integers, a bag of real numbers. It could be a bag of strings, actually, etc. Okay. It could be, well, okay, sum. So if I give you a bag of integers, can you sum them? Yeah, you can sum them. If I give you, can you make an average of them? Yeah. Can you count them? Can you count how many there are? Yes, you can count how many there are. Can you calculate the min and max values? Sure. Okay, so let's look at this right here. So if I say, we have A and B here. So if I go over every tuple here and I do a sum over A, then I'm going to get 7. I'm going to count, I'm going to get 3, and the max and the min. So it's pretty clear in terms of how that goes. Now, here's where it gets a little bit more tricky. Here's where it gets kind of tricky. So we have the gamma operator, okay? And I probably am going to go over to, the way this gets, this is a good question. The way this gets, this is just kind of what you write down in the actual query expression. So I hope that this will be cleared up in just 1 second here. So what we have here is we have the gamma operator. It's just like a select operator. Well, I mean, it's the same kind of, well, it's not just something. Don't quote me on that. It's like where does the select operator come from? Well, you write it down. Okay, so we have a gamma and then we have L. So we have basically 2 types of elements in the L list. We have individual, or what's called grouping attributes, and then we have some aggregate function or aggregate operator, it's called, which is over an attribute. Okay, and then an arrow gives that renames that particular component. So let's look at an example here. Let's hope we get an example here. Otherwise, I'm going to have to. All right. Yeah, let's just look at this example right here. Okay, so we have the relation R, which it has the attributes A, B, and C, right? And then we're going to basically say gamma A, B, and then the average of C. Okay, so what does this mean? All right, so the gamma, maybe what I'll do now is I think I'm going to just go over to the camera. And then I'm going to yeah. Okay. So let me know if everybody can see if this is coming out well enough in terms of. I mean, I'm watching the chat here. If people say that it's blurry or the light needs to be. I can. Okay. Let's just go to this example here. So we have R, A, B, C, and then we're going to have. Let me start off with a simple one. 1, 2, 4. I'm sorry. 1, 2, 3. Okay, I'll make it exactly the same. 4, 5, 6. 1, 2, 5. Okay, this is good. Okay, so it looks fine. I can make it even better though. In fact, I think I will. I'm assuming this is even better. Of course, you might say, oh, it's worse. Okay. All right. So let's do a really simple one. Okay, let's do a gamma. All right, there's our gamma. And let's do a kind of even simpler. A, and then I'm going to basically say sum of B, and that's going to apply over R. All right, so this gamma is the grouper. It's the grouping operator, okay? And there are in this case, two components under the grouper. There's the grouping attribute. In this case, we only have one, so it's a simpler case. We have one grouping attribute, and then we have an aggregate operation that we're going to apply to the groups that are resulting from the grouping operator, from the grouping attribute, rather. Okay, so what does the grouper do other than group? Okay, so what the grouper does is it looks at the attribute A and it basically says, okay, how many different values, and let me get in the checks, how many different values do I have for A? How many different values are there for A? How many different groups are there for A? Well, there's the group here. I'll go over here and I'll say there's group number 1, okay, which has the value 1, and there's the group that has the value 1. So here's one group, okay. I'll circle that, and then we have another one for 4, okay. Now that's what it's done. So basically, what it does is it partitions the set of tuples. It partitions them based on their values of the grouping attributes. In this case, there's only one of them, A. Okay. So when I say partition, it's going to break these into sets or bags, if you will. They're bags. Actually, there are bags. Okay. So this one owns that, and it owns that, and this one owns that. So the count of the group that's 1 is 2, and the count of group 4 is 1. Is everybody following? Because we're just really going to we're going through this in a very, very kind of painstaking way. Okay. Now that it has the groups, so basically it has this is the group for 4, and this right here plus that is the group for 1. Now, what it's going to do is over these. So basically, it's what the grouper's done is it's kind of partitioned the table into a whole set of like virtual tables, if you will, or groups, basically groups. So what it's going to basically do now is it's going to say for group number 1, it's going to basically add B and B. So it's going to basically equal 4 here, right? So the result is going to be for this right here, this right here, when I do this, so I should do it this way. This equals, so this yields we're gonna have 1 and we're gonna have 4, right? Because those are the A's for the different operations. I'm sorry. Is this the operations that are used? Oh, I'm sorry. Well, yeah, it doesn't matter. The answer is no, absolutely not. So, somebody said, is this the operations that are used to solve 4 and 5 in recitation number 1? And the answer is absolutely not. You have to solve those in recitation number 1 using the pure relational algebra. Okay, so if you start using group, if anybody pulls out a gamma during recitation 1, you should not come up with anything in the expanded relational algebra. It's all going to be based on the pure relational algebra. So I don't want to see any gammas in recitation 1. All right, no gamma in recitation 1. I hope but it's a good question because it allowed me to get my soapbox here and make a demand. By the way, I hope that everybody's clear about the mechanics of recitation 1 and how you guys do your claims and uploads and all that stuff. Put some questions in the chat if you have any questions about that. Just want to make sure that we don't have any weirdness on that. So, okay, now group number 1 consists of these two tuples, and I'm going to do a sum of B on that, and that's going to wind up being 4. And then the sum of B on group number on the group with 4 in it is just going to be 5. All right. Now, then there's a question of this, like, well, what attribute in the resulting relation here, what attribute is this? Is it an attribute? Could we call it some B? We don't want to do that because that's an. If I do this and I say we're going to rename that attribute, so the arrow right here inside the grouping operator, what this arrow does, it does the renaming so that we get the name of the attribute to equal to C. Okay. So that's it. That's what the grouping operator does in the extended relational algebra. Now you might say, all right, fine. What kind of things can this solve for us? This gives quite a lot of practical power to the language. And you'll see in SQL that we actually have a group by construct in SQL. So we that's essentially that's basically equivalent to this gamma operator in extended relational algebra. So we're gonna do a lot of this with SQL to kind of build up your intuition. Let's see if I missed anything here. Okay, so the arrow does the renaming. We applied R according to grouping attributes. Okay, R according group all the tuples according to the grouping attributes. All right, so that is, you form one group for each distinct list of values for those attributes in R, and then within each group compute the aggregate function over that group, and then the result has one tuple for each group. All right, so one tuple comes out for each group. The grouping attributes and the groups and the group's aggregations. So that's how, yeah. So that's essentially how that works. Now, if we go to this example here where we were actually doing a grouping on AB, then our groups are going to be defined by the group of 1, 2, and then the group of 4, 5 in a purely analogous way, and then the averaging is going to be computed, over those groups. So we basically, so the green here group is the 1, 2 group, and the red, or the whatever that is, red, magenta, whatever it is, 4, 5. That the 4, 5 group is that one there. There's only one tuple there, so we just do that grouping. We get the average of 3 and 5 is 4, and the average of 6 is 6. All right. Okay. All right. Got a question here. Let's see. Let's see. C equals. All right. C equals 4. I think you're talking about the example I did. It's because there were 2 2s in B. Good. Yeah, it looks like you guys answered it yourself. You are still sharing the paper. Thank you. I'm never gonna learn. All right. There's one. Yeah, I was sharing that. Oh no! My laptop. My laptop was almost ran out of power. It's plugged in. Okay. Yeah. So I just kind of like went all through this right here and just kind of reiterated that to make sure we didn't lose anything or miss anything. And then I showed this example here where the red is the 4, 5 group and the green is the 1, 2 group, and then. So I hope this is pretty clear. And then, it just really bugs. I'm sorry. It really bugs because I lose then the chat. Okay. Okay, yeah, and that's it for that. So why don't we do the following now? Because what we're going to do now. Okay, first of all, are there any questions? Does anybody have any questions on this stuff? Okay, don't see any questions. Why don't we do the following? Can we be back at 11:05, and then at 11:05 we're going to start in on SQL. All right, we're going to start in on the something that you can actually use rather than just this kind of more formally defined stuff. So, but the key thing to understand is that SQL is translating itself into this extended relational algebra. So it's kind of the extended relational algebra. It's not. It is used. I mean, it's definitely something that goes on. It's worth knowing. So, all right. Why don't we get back then at 11:05 and we'll resume with SQL. So, okay. All right. See you guys then. Unless there's questions here. Oh, one second. Does Gamma always delete duplicates by sorting? Yes, you could say so. Yeah, because the groups are you could say the groups are kind of under a set semantics. Yeah, so it will squash down all the duplicates. So I mean, if you did, I mean, what you might say then is this: is that do I really need the delta operator? When all I would have to do is I mean, when I use the delta operator that removes duplicates, that's actually equivalent to me doing a gamma operator where I name all the attributes I have no aggregation function, but I name all the attributes in the relation. Okay, so that one's what we're going to say. What knowledge do we need to lab one? SQL. I mean, lab one is the SQL lab. Okay. So, all right. If there's any more questions about that, right? But, okay. Otherwise, okay. Let's get back here at 11:05. I'm gonna get some coffee, and then we're gonna go into SQL, which is what is needed for lab one. I got a private chat here. Private message. Okay. Right. So let me pause recording. Okay, pause. So now we're resuming recording here, and let me do a share screen. Okay, so just what you've all been waiting for. Now we're finally getting into SQL. And one sec here, I just want to make sure that yeah, I got that set up. All right, good. All right, so and then once again, it is annoying because I need to explicitly open the chat because it disappeared. All right, now we're good. All right, so anything, just put anything in the chat now, I can read it. So, all right, so let's resume here. Why SQL? Okay, so SQL, let's just go through a little bit of what SQL is about here. Okay, so it's a very high level language. Remember that the basic thing was that tuple calculus is kind of declares what you want. Relational algebra says how you do it. Actually, how do you calculate how do you apply the operations to relations and yield a relation that has your answer within it? So this is like saying what to do is what's called declarative, and then how to do it is procedural. And the truth is that SQL is kind of a mix of both, right? So it's a mix. It has relational algebra aspects also embedded within it, so that you can actually kind of make it. You can kind of tell it how to do it, not just say what you want. It avoids a lot of the data manipulation details like a procedural language like C++ or Java. Yeah, so I mean, another option, of course, to databases, and this is the option that maybe computing systems started with in the very, very beginning, is they just said, we have data, and we're just gonna have a program that goes in and accesses the data using a standard programming language like Python or C++ or Java or something. So, I mean, the problem with that, though, is that there's a lot of reasons why you don't want to do that, but that's using a Turing-complete language to get access to the data. I mean, there's a lot of reasons why you don't want to do that. Maybe I won't move too much into that at this moment, but I hope that people can understand that if you do that, then it's just like you're basically having to reinvent the wheel every time you have a new application. So databases kind of save a lot of labor in terms of getting kind of a standard way of getting access to data. and SQL is the language to do that. Let's see here. Yeah, so the standard story is that the database engine, the optimizer, is what's going to actually determine how it answers the query. So you put in the SQL, and it does a lot of its own, makes a lot of its own decisions about how exactly it's going to do that when it translates that to the extended relational algebra. And that's called query optimization. Okay, so SQL is kind of like tuple calculus plus relational algebra. So it's using both tuple calculus and relational algebra concepts. And then when I say the relational algebra, I mean the advanced relational algebra, and a lot more, a lot more. So aspects of the tuple calculus, there are variables, couple variables, and like it exists. You have the backward e symbol, but you don't have a universal. All right, but we'll see that you can simulate it. You can get a universal by having a double negate exist, negate exists. Now I'll kind of go into that. So exist is enough to basically capture the universal when you have a negation. All right, aspects of relational algebra, yeah, all the basic operators made practical, bag semantics, updates. Okay, so it's got a lot of other stuff that we don't really treat in the. So I mean, one of the questions, of course, in relational algebra was that like, and also the extended relational algebra for that matter, was like, yeah, this is just reading the data. What about adding data in, modifying data, etc. So SQL has those kind of those aspects, and it has like a real treatment of data types, and it has a lot more aggregation operators and arithmetic. There's a lot more functions you can apply to data. So I mean, SQL. A lot of things have grown up around SQL. Excuse me. So it's kind of complicated, and one of the things also with SQL is it always depends on what system you're using. So there is an SQL standard, but then what happens is that really a lot of the more extra features become very specific to one database system implementation or another. Lots of built-in functions. Okay. So traditionally what you do is you divide the SQL into like the data definition part of the language and the data manipulation part of the language. All right. So this is where the DDL, the data definition language, is where you actually define the tables. And also what are kind of known as views and the constraints. That's all gets put in the DDL. And then the DML is actually where you do the select queries or the update queries or the inserts or the deletes, right? And plus some other stuff as well. So let's do some examples on the computer. All right, so I'm going to switch over then to the computer here, and let's see if I can. Let me see if I can do this in a way that is going to make some sense. Yeah, I'm just trying to think what editor I want to use. Yeah, I'm going to do it. Okay, I'm going to stop sharing. Oh, actually, no, I'm not going to stop share because this is I'm sorry, people. So what we're going to do here is on the computer, I'm going to basically do, I'm going to show relational algebra inside of SQL. I'm going to show tuple calculus inside of SQL. Then I'm going to show some of the syntactic sugar in SQL. And then some of the stuff that goes beyond tuple calculus and yeah. And so this is just how I'm going to organize the presentation. So okay, let's just stop the share. Okay. And then I can just get rid of that. And then what I can do is I'm going to fire a PyCharm, which maybe I should have done earlier, but I didn't. Okay. And then let's just take a look at this first. Okay, sorry about the delay here, everybody. That's all. Okay, so I'm sure everybody can, I'm assuming everybody can see this. So this is this Northwind database. And let's just look a little bit at kind of what's in this database here. This is the actual DDL. So this is the data definition for this database. So just get myself a chat here because I lost the chat, of course, as is typical. All right. So now I can see the chat at least. All right, so what we have here is we have like the tables are being defined. So we have the table of like these categories for these products. And then we have like this is the customer table. So it has like the customer ID, which is not null. Then it has employees, has order details. This actual owner thing, I'm a little bit surprised that's in there. That shouldn't be in there. I should, anyways, products, it's like for shippers, suppliers. So it's, and then here, these are kind of bulk inserts that are common. This copy here. This is very specific to PostgreSQL. Anyways, let me just go here because I've already built this database. Although I haven't. Now I'm a little bit worried that it's not going to do what I want it to do. But let's just take a look here. Okay, so all right. So we're here. Here we are in this basic. Let me just take this up from the top because this might actually be helpful for people. Drop DB Northwind. Okay, now we're back. So there is no database now. So if I say like PSQL Northwind, boy, the database does not exist. Okay, so I'm here. I'm in Linux here. This is my my Linux shell here, and I'm not really sure what you guys are using, but this is kind of how I'll just kind of show you how I'm going to go about doing this. All right, so this is what I'll do is say create DB. What do we want to call this thing? Let's just call it Northwind. Okay, so then we have Northwind. Hit up arrow twice, and then backspace. Now I can actually get into that database. Okay, so let's see here, DT. So this right here is PostgreSQL, a PostgreSQL way to list the tables, and there are no tables because it's an empty database. What do we have here? Got a question here? Okay, yeah, I think I'll actually answer that a little bit later. I had a direct message here. I'll take that up later. It's not a very important distinction. So I would just use varchar. Anyways, what do we got here? All right, we have nothing. All right. So what I'm going to do here now, this is just again. So if I look right here, we see the northwind.sql, which is this file right here. Let's load that puppy in. Let's just go and load that in. And I hope that doesn't cause me any problems because of that owner MJM, but it might, but then we'll see. PSQL Northwind is the name of the database. And then -f means bring in that file. And it's the file Northwind. Okay, seems like it worked. Or no, it didn't. But it didn't really care. I don't think it cared. Normally when you do so there's a PG dump. I mean, there's a lot of little things to say about that, but anyways, the MGM should not be in there. I should have, when I did the dump of the database, I should have said no owner, so that it doesn't like actually have an owner role there. Roles in SQL and users in SQL, that's a whole other thing. It's pretty simple, but it's just the way it is. And so it's one of those things where I don't really, you can learn a lot if you just kind of go out and read about it. So it's really simple. Okay, so anyways, let's just go into this right here. Let's go back into the database here, and then hopefully now we will actually have tables. Yes, we do. So we have 6 tables. It says 8. I'm sorry, we have 8 tables. It says 8 rows. So actually, what's happening here is that PostgreSQL has a database of the database, by the way. So that's kind of why it calls it rows. There's an actual table inside of PostgreSQL somewhere, that represents that has as tuples each of the tables. So that's just kind of, it's an abstract model of how PostgreSQL does stuff. But let's just kind of, all right. So if I just let's do some real simple SQL just to get, okay, let's just look at a table. Okay, select star from let's say employees. Okay. Now, here, this is a common mistake. I'm not sure how many people have gotten to this kind of thing with SQL yet, but okay, I hit return. Why, can someone say, why isn't it working? Well, I can beat you to the answer. You have to terminate stuff with a semicolon. All right, now we've got like, you know, we have all the information is coming back now. So we have 9 rows. There are 9 employees. Let's do this. Let's say D plus employees. Right. This actually, let me make this a little bigger. The D plus will actually give us information on the, that's kind of annoying. Let's see. All right. When you do that, it will give you information on the table, like what are the attributes of the table. So let's just do a really simple, let's do projection. Okay. Let me do first name, last name, and title. Okay. So here's projection. This is equivalent to a project. What was it? What did I say? Well, we can look right here for employees. I said project first name, last name, and title. Okay, so first name, last name, title from employees. Okay, completion. Okay, so this right here, that's an example of just projection, right? So we have Nancy, so let's see, do we have anything that's duplicated? Yeah, sure. So now if I do this, now what happens if I do a different projection? Let's say a projection, I just do title. What am I going to get back here, people? What is going to come back if I just do title? Is it going to come back as a set or as a bag? It's going to come back as a bag, right? So it's doing the duplications. What if I want to turn it into a set? Then distinct is what does that, right? Let's see here. I want to open up a different file here. Open, and then let's do real. All right, so here's some examples. So these are some of the examples. Selection. All right, so selection would be something like this. I could say select. Here's a simple projection that is select distinct city from employee. Sure, that gives us the sets. Select distinct. Now distinct always will turn things into a set. So that's how we get a set semantics. And this right here is basically going to be our selection operator. So this is equivalent to selection. So unfortunately, select in SQL has nothing to do with select in the relational algebra. They're kind of applying to different things. Select in the SQL has to do with like basically projection. It has to do with what attributes are going to be picked here. Okay, so let me just kind of grab this, copy, and let's just paste that in. All right, so we have that. So this gives us all the ones that have units in stock above that amount, above 100 units in stock. Say, okay, let's try this for like 1,000. Is there anything with 1,000? No. Is there anything with 400? No. 300? No. Huh. That's annoying. Okay, 8 or above 110. Let's see how many units in stock do we have there. Looks like a 130. That's it. Okay, so if I say above 120, I'll get just a couple. Yeah, look at that. Okay. Oh, I'm kind of hungry. Lunch is coming up. Crab meat. That sounds pretty good, actually. All right. Let's see. Okay, so that's pretty okay. Now Cartesian product. Now see this right here. If I say now there are 77 products in the database, and there are 8 categories. So if I just do this right here, I just take 2 tables in the from clause, because I mean, if I didn't say SQL is all built upon select, then you name a set of attributes or aggregate functions or whatever it might be, then from, and then a set of tables, and then where is a set of conditions. So if I say this right here, if I say, this is going to give us back the full Cartesian product. So 616 rows. And you can verify that by basically doing the simple calculation. 77 times 8 is equal to 616. So, okay, so it just gives us the full Cartesian product that way. Now, you can use, now I've really never seen this. Some people, so okay, I mean, the thing is, it very quickly gets kind of messy with SQL, but I mean, there's like 1,000 different things I can say here, but basically, you can put your joins. See, we have the notion of a natural join here. This is kind of interesting. What you can do is there's a special syntax in SQL where in the from clause, you can specify the join types, right? So you can say something like natural join, you can say cross join. I've never seen this in practice. I've never seen anybody ever use this thing where it's going to do a Cartesian product. This right here is equivalent to this, just putting a comma there. But natural join, I've seen that sometimes, and I've seen this theta join a lot. And a lot of people use this syntax where what they do is they'll go through and they'll put in the join, they'll specify the join clause, the join conditions inside the from clause. Now you can actually wind up doing that inside the where clause as well, but you'll see that people will put them in as natural join. You can even have outer join. Now remember, I forgot to cover outer join. I need to make a statement. I need to make a note of that. Outer join. I'll cover that in relational algebra. All right. We have the natural to natural join. Consider taking one of the sets from both. All right. Then we get into some like little tricky things in terms of like, what we have here. All right, this is kind of, I think, something interesting to talk, or a little bit interesting to talk about. So this is something that you can do inside of SQL. You can have, this is this is like basically some subqueries in the from clause. So this is actually what kind of allows us to kind of stack these things up as these kind of giant expressions. So what does this thing right down here do? This right here says select the category name and the product name from, one sec. Okay. Let's just look at this right here. All right, let's just take a let's put this one under the microscope. All right, select category name and product name and the product name is going to be called a SWP name, so like a Swedish product name, from categories, natural join to products, all right? And then that's going to be also natural join to suppliers, where the supplier is the country Sweden. Okay, now let's see if I can bring something up here for us to kind of see this kind of diagrammatically. One sec. I hope this can be seen. All right, do people see this thing? I hope this is coming. All right, so let's see what's really happening here. All right, so what we want is the category and the product names for the Swedish products. Right. Well, how does a product become Swedish? Here's product right here. Right. Here's a product, and notice here we have supplier ID. That's a foreign key into supplies. And notice that these are named the same thing, supplier ID, supplier ID. Therefore, we can do a natural join between these two tables. And when it does a natural join, how many attributes does this share with this? There's only one, supplier ID. And so what it'll do is it'll enforce equality on that, and then it'll only copy one time in the resulting table. And then it'll bring back, and the total number of attributes in the table that does natural join is however many attributes here plus however many attributes there, minus one, because supplier ID gets kind of brought down into a single attribute. and there's equality enforced on it when it does the join. Okay, I hope that makes sense to people. And then, so by doing that, you can get to Swedish products. Is what you do is you just do the natural join between products and suppliers, and then you put a selection, in the relational algebra sense, you put it in the where clause in SQL sense, you put in the country equals Sweden. All right. And that whole thing can also be natural join with the categories, and category ID here and category ID here are the same attribute. So, and that's the only ones that they share in common. And there you can find the category name that way. So we're going to do a natural join between products and suppliers, and then a natural join between products and categories. And then we're going to do a where clause where we make the country equal to Sweden. And then we're just going to project out the product name and the category name. All right. And that's exactly what this query does right here. Okay. Doing natural join from categories to products. Oh, wow, it's doing a little bit opposite direction here. So categories, natural joins with products, and then natural joins with suppliers, but then the supplier's country is going to equal Sweden, and then we're going to project out the category name and the product name. And then we're going to do what's called aliasing, where we're going to name the product name SWEP name. Okay, all right. So is that clear to people? I hope. So let's see what happens when I execute that thing. Well, grains and cereals gives us Gustav's knäckebröd, and then we have inlagt sill, gravad lax, and röd kavre. These all sound like Swedish food, I think. All right, I've eaten them all. Again, I'm getting hungry. This is 30 minutes until lunch, people. All right. Okay, so let's see. Any questions? All right. So I hope that was clear. Okay, so this is just this thing right here. This query here returns this table here of category name Swedish product name. Now, what I wanted just to show inside of here, though, was all of that can then become this table here. Whatever table that's coming back right here, we're renaming that table to Swedish products, and then we're just doing, we're just selecting out the Swedish product here. But the idea here, or the point of this, if I do it this way, the point behind this query here is that I calculated kind of like a subtable within the query itself, and then I was able to do operations over that. So you can imagine that you can get some pretty complicated SQL this way, and you can do some pretty powerful things in terms of like building up these giant expressions that do quite a bit with inside them to kind of pull out information and join and do other stuff. So yeah, so there's lots of SQL floating out in the quote real world that wind up becoming these things that have these sub queries wind up being in the from clause, right? So that's something to know, that you should be aware that you can do that. You can also put subqueries in the select clause, but sometimes it becomes a bit more tricky in terms of what can happen when you do it that way. Okay, so I hope that was clear to people. These things right here. So what is this doing right here? Select city from suppliers, union, select cities from employees. Yeah, this might actually work like looking at for a second. So this is one of those quirks of SQL. So there they all are. Oh, there's my hometown, Ann Arbor. That's where I'm from. Okay, and then that was my stomping ground. Okay, so but you'll notice here this is a set. There's no duplicates in here. But if I do this, if I say so, if I say this, if I say select city from suppliers. Oops. You'll notice here that, let's see. I'm a little bit surprised by that. One sec. Okay, from suppliers, from employees. There we go. Yeah. So that right there is a bag, because London is coming back here. We have 4 Londons here. But then what's weird is that when we union this, that we'll only have 1 London in the result. Where's it, London? Somewhere here, London. Here, London, London. There's London. Okay. So what this means, what the reason why this happens is because SQL in its infinite wisdom decides that when it does a union, it's going to do the union under a set semantics. Okay, because so this does make union idempotent. It was a design decision that was made, but it's just a quirk that you should know about SQL. Let's see, what if we want to get bag semantics under the union here? Well, then what you do is you just basically do this. That tells it to ease up and let the duplicates go through. All right, so yeah, okay. So that's essentially recording SQL. Okay, and I think that is in this file here. Okay, union, yeah, exactly. Select except all. All right, so the set difference is done via except. So there's no difference and there's no minus operator. God forbid, because that would confuse the parsers enormously. Like there's like not, you know. So you have except. So except is like set difference in SQL. Intersect, the same thing. And these also have the same kind of structure where to get the bag semantics versions, you have to put the all this except all inside the expression. That's just the way it is. Yeah. Okay. Here's the thing. You will see people using these things. Let's see. Let's see if I want to play a little risky here. No, I don't want to play risky. I'm just going to keep it there. Okay. All right. I don't see any question coming up. So let's just keep on going. Oh, okay. When doing natural joins, do they need to have the same name? Natural join between 4 and 2. Yes. If they have the same ID but different names as an organization, that's correct. That's right, exactly. So I had a really good question here. I'm going to not say who it is, but I'm just going to read it out. Okay, when doing natural joins, do they need to have the same name to do the natural join between the foreign keys and the key where it's being linked? Yes. If the name is not the same, then it won't work, or it'll work, but it won't. It'll basically revert it back to a Cartesian product. All right, which I'm sure is the I'm sure that's caused like hundreds of millions of dollars in people messing that up. That this has resulted in untold amount of damage to the economy. I'm sure it's a common mistake people make is that they do a natural join. Oh, why is this thing not work? Why are so many tuples coming back? Why are so many tuples coming back? Because the natural join isn't matching on the names, and it's just giving you a Cartesian product, and it's not being very nice about it because it's just doing it, and you're getting these giant queries, and you don't know why, and yeah. All right, and in the recitation, the names are different. That's right, the names are different. Thus, the natural join is not going to work. You're going to have to use a theta join. All right, but you're not doing any of that because if you're doing relationality. Right. Is there a difference between capital select from? No, it's case insensitive. SQL is case insensitive. Actually, what's a good convention is to always capitalize the keywords of SQL and then have well, this is actually the correct convention. You will capitalize the first letter of a table, and then you keep the attributes lowercase, and you capitalize the first letter. But then you have all capitals for the actual keywords of SQL. In recitation 1, you're going to use set semantics, no bags. That's the way it is. Because remember, core relational algebra is set-based. Core relational or the basic relational algebra, the kind of historic relational algebra, the mathematical relational algebra is based on kind of these mathematical notions, and it's set-based. So recitation 1 is set-based, set semantics, not bag semantics. Okay. All right. Let's see. Okay. Let's go on to the next file here. Where's my Python? There it is. And then let's go to the tuple calc. All right. And move this puppy over here. All right. So now let's do a little bit of tuple calculus inside of this. So relational algebra. Let's do some tuple calculus. All right. So this is under set semantics here. So basically, select is okay. This right here is, this is just like open set marker x dot product name such that marker products of x. That's what that is. So that's a simple projection inside of or simple, pulling out the first component of the products, each of the products. All right, so here's what we have. This right here says, all right, give me the products where there exists. Okay, so this is like this is couple calculus here because what it says it's saying, give me products where there exists a y, where the y is a supplier, and the y is supplying that product, and the y, which is a supplier, is from the country of Sweden. So this will give us the products that are, and it will give us the distinct product names for the products coming out of Sweden. That's what this will wind up doing. And notice how it is a tuple calculus, because what it's basically saying is it's using this exists. So this exists basically says, this is the exist y, basically, right there. Okay, so that's, let's just verify that works, and it does, of course, point, and then there, yeah. Boolean operators. Okay, so you can put or in here. So this will give us the products from Sweden or Norway. So let's see what the Norwegians can contribute to the feast. Okay. So some kind of cheese. And some kind of goat cheese. Oh, so they're giving us cheese. Distinct keyword will not return to. That's correct. So distinct is what turns it into a set semantics. So I mean, it's just because I'm doing the tuple calculus here, so I want to make everything set semantics based. So that's why I put distinct on everything there. Okay. Good questions. All right, here's another way of doing it. So you can do that as a disjunction, or you can do it as a set operator. So where the country is in the set of Sweden or Norway. All right, so that is done this way. So this should give us the same result. I almost pasted that into the chat. All right, same result. Okay, not exist. All right, so what is this going to say here? This is basically saying this. It's saying give us the categories where there does not exist. Okay, so basically what this is, let's put this through the English paraphrase. This is give us the, the categories that are not represented, or the categories that are not Swedish products. Right. So it's basically saying, give me the category. So what's a category? Let's just do a select star from categories. Beverages, condiments, confections, dairy products, meat, grains and cereals, meat, poultry, seafood, and produce. Yeah, I will upload these to Canvas. I have to check though. Yeah, I will. I just have to make sure that, yeah, I'll upload them. Oh, anyways. It has to do with lab 1, which, yeah, anyways, I haven't decided on lab 1 what database we're going to use. I mean, I most likely will use Northwind for lab 1, but I'm toying with the idea of bringing it in. But it all depends on what I can get time. And also, yes, I'll upload these. I promise. Later today. Let me just make over that. Okay. What do we got here? We got. Okay, so what is it saying here? It's saying give us the categories where there does not give us the categories. So it might be something like confections. Right? And actually, I think confections will make it into this answer. So give me a category where there does not exist a product of that category, which is being supplied by a supplier in the country of Sweden. Right? Does that make sense to people? Let's read again in English. Give me the categories where there does not exist a product of that category, where that product is being supplied by suppliers in the country of Sweden. Right? So how would I really say this in English? I'd say which categories are not being, what are the categories where Sweden is not supplying the product? So let's where no supplier in Sweden is supplying that product. So I think that seafood is definitely not going to make it because we have Gravat locked. So yeah, so there are no beverages, condiments, confections, dairy products, meat or poultry, or produce in this database, which are being supplied by a Swedish company. Okay. All right. So now, what about this? So what is this saying right here? Okay. What this is basically saying, this is saying, okay, give us the employees where there does not exist a shipper where that employee processed an order where that shipper shipped. Okay, so this is like saying, give me the employees that have processed orders for all the shippers, all right? So let's just think this through here. Give me the employees where for every shipper in the database, there's some order in which that employee participated. So this is a very experienced employee who's dealt with all the shippers, right? But SQL doesn't have a for all construct. Instead, you have to contort it into, give me the employees for which there does not exist a shipper where there does not exist an order where the employee was the processor for the order and the shipper was the shipper shipped for that order. Does that make sense? So this is the kind of duality in logic between existential and universal quantification. So if you have negation, you can always replace all your universals with existentials under negation and vice versa. So if you have exist, you can always replace that with a not for all, not. So it's when people talk about duality of operators of quantification and logic, they're basically talking about this kind of strange flipping that you get, or the fact that you only need universal or existential plus negation you need existential plus negation to simulate universal, or you need universal plus negation to simulate existential. Okay, so yeah, so this is represented now in SQL. So the thing is that this is actually not the most efficient way of doing it, but it's good to know this. Let me see, does this ever come up? Yeah, this comes up actually, I take that back. This actually is kind of good to know how to do it this way. So this actually has come up. Yeah, I mean, I've actually done work where this has come up in like the quote real world. Like for instance, if you talk about like, okay, here's an example. If you talk about recipes, so let's say we have like a database that has a bunch of foods, a bunch of recipes, and like what foods belong to the recipe, right? And then also we have another table which says what do we have on hand. You basically you can only make a recipe if all the ingredients of the recipe are in the refrigerator or in the pantry or in the kitchen, right? So this comes up, that replicates itself in many different cases. So like if you need to apply an operation, let's say that we have some specification of some kind of chemical or industrial process we want to apply on something, but we can only, but there are a set of things that are needed you need to have a certain set of machinery and materials on hand to apply that process, right? Then if we want to compute this, like given a particular factory situation, we want to compute what are the operations we can carry out, we need to basically represent it as this double negation, because we need to be able to say, give me the operations where there does not exist a material in that operation for which there does not exist a record of us having that material on site. You got it? Okay, because that's this does come up. This comes up, kind of some more advanced modeling type applications. It does come up. Now the thing is that a lot of times what will happen is the way you compute this is you use aggregate operators and you do counts, and that's actually more efficient too. But it's good to know this. It's good to know. these kind of for all type constraints or the need to represent for all type situations comes up in advanced applications. Yeah, quite a bit. I hope I made the case for that. So this is what we're kind of looking at. Okay, good. All right. So that, I mean, so the tuple calculus is so simple. You know, we were able to cover that. That was all right. So let's go on to the next one. And that is going to be. Okay, so this is like, when I say sugar has syntactic sugar, which is stuff that's just added to SQL to make our lives easier. All right. Okay, so this is something that's really dangerous. dangerous. Well, this is trouble. This is real trouble. Why do I repeat that exactly? That must be just be. Oh. Well, that's because this is going to turn null. All right, so you can do this, and I don't suggest you do it. In fact, I'm going to say that I'm going to notice what's happening here. Give me the company names from suppliers where the city equals, and now we're going to find the city where Mason Dewey is or whatever, right? So this returns, but the thing about this right here, this could return, in principle, if there was like several companies named Mason Dewey, this could return a set, right? Why don't we have universal and tuple calculus? No, I'm sorry. It's in SQL. So I have a good question here. Okay, why don't we have universal in SQL? We have it in tuple calculus. We have extents in tuple calculus. The reason is that I mean, they made a lot of kind of rash decisions about the initial SQL syntax, but the reason is mostly, I think, that they wanted to kind of simplify the implementations. They wanted to simplify the implementations. And because I mean, SQL's already got a lot of syntax going, you know, SQL. If you you know, if you hear some mathematician kind of bad mouthing SQL, saying about how junky it is, et cetera, then you basically say that then, because I mean, SQL is a higher order logic. All right, SQL is using higher order logic. That's what it's doing. It is so higher order logic means you can basically quantify over sets. It's using it's a very expressive language. But it's because of that it results in kind of a lot of uncontrollability of the syntax and semantics for that matter. Because higher order logic is it's really elegant, it's really cool, but no one can make any sense of it. It's very simple to write it down, but it's very difficult to work with. That's why the logicians stay with the first order. I mean, they work on the easier problems, because it's just become so intractable to kind of deal with higher order logic. Now, of course, there's been a lot of research in higher order logics, and you know, it's interesting. It's interesting work, but it's always kind of a syntactic mess. So I think that SQL they just said, well, we'll have this existential because you know, exist and not exist, because we don't. It's already going to be complicated enough doing what we're doing. So we don't want to complicate the syntax even further by putting in an explicit universal. So I hope that answers that. And anyways, getting back to this business here, is the problem with this is this right here is very bad, because you can't, this will actually run, because oops, well, there is no Mason Dewey. So okay, let's say there was one. This one, and there must be a reason why I have both of these. Excuse me. The problem is this in this particular case here. Yeah, I'm gonna have to go check that. The thing is that this could be something like, oh yeah, here's an example. What about this? This is going to basically have a single value equaling a set of values, and I believe this is going to give us a runtime plop. Yeah, see, look, it belly flops on this one because it's more than one row return. Okay, so basically this is returning a set, and it's saying does this particular single value city equal that set? So it sees that there's like this kind of mismatch of basic categories, types. You know, this is a set and this is a single. It's like it doesn't know what to do with it, so it does properly return an error. But the problem with this is that you're basically doing kind of runtime checking, And these are particularly bad kind of errors because maybe somebody kind of works let's see, customer city, select city from customers or company name. So this is going to bother me here. 1 second. What company names from customer city from customers? All right, give me okay. Where company name equals is that Alfred's, whatever that is, maybe. Oh, I see. I think I see the prompts are on here. So actually, this is returning. This actually, oh, sorry. I should find one in London or something. This actually is returning a result. Okay, Brussels. But then the thing is that there's no company name that's in that city. That's the thing. So it's returning this value, and then it can do kind of a direct, match on that. It's doing it in this case. It's returning null because there is no city, no company with that name. In this case, it's returning a whole set of them, and that's where it busts down. So these are problematic, and the reason why this is problematic is I got some questions here. The reason why this is problematic is because it busts down at runtime, and you would prefer, and so somebody might code this thing up, get it to work in a particular instance of a database. Then somebody changes the state of the database, and the program that was using the SQL is now busting down. That's not good. You would like to have it so things are a bit more robust. So this can lead to a lot. This is really problematic to kind of use this, but you can. Then you have in. This right here returns a set here. This is kind of like a tuple. Don't do this. Sorry. Please don't. I mean, actually, I should say that instead of sugar, I should say avoid. Don't do that. I mean, generally speaking, I mean, the most really annoying aspect of some. Here's the kind of technical person you do not want to be. I'm so brilliant. I've studied all the intricacies of this or that inside the programming language, and now I'm going to do this really kind of esoteric use of in a particular PostgreSQL. I can do this thing, and it makes perfect sense, and it works perfectly in PostgreSQL. And this was I was special knowledge I used of the internals, and I'm really kind of pushing. It's like, please, don't be that tech person who delivers really obscure but correct code, and then you go to that person, you say to them like, what is this doing? Okay, I know it works, but why? Like when I get code delivered to me, for more industrial side of things, if I want to please keep it as simple as possible. Thank you very much. Don't use esoteric aspects. Keep everything vanilla. Thank you. That's what you want out of it. Out of really good tech people do that because they know that their code is going to get reused, and maybe not everybody is as enlightened as they are, understands these deep things. At the same time, of course, it's a trade-off because if you do know kind of a short way of doing something, it's a little bit more obscure, but it really is much better than go with that. But it's kind of a trade-off. But don't dig around and find these weird things like doing this. Please don't do weird stuff. This is weird, and this would get me very annoyed if I was the boss who had to integrate this later. Not the boss, even the boss, the coworker, whatever. When people kind of start doing this kind of stuff, it's annoying. And then you confront them, and then they sit there and they think that then they treat you like an idiot because, oh, you don't understand, you can do this. That's SQL. It's like, yeah. Not good. Okay. Anyways, let's see here. I hope that I got enough of my pet peeves. All right. The any and all. I think that almost qualifies under that. The any and all. I mean, you don't need to use this stuff. I mean, of course, I have used any and all. I have, but in very particular cases. So what this basically says, it says where the country equals. You can do this with a natural join. You can do this with a join. So just do it using common. Try to reduce the variation in the way you solve your problems so that you have this uniformity over your code. That's another thing. You want to have uniformity within the code you deliver. Because then if someone wants to understand what you're doing, they read it and they say, oh yeah, this person is applying this same kind of pattern all over the place. But if the person is applying needless variation to all the different problems, but it's all doing the same thing, and they could have had just one way of doing it. That's not good. Okay, so anyways, any and all, I think you're almost always going to be able to do this with a join. So only when you're really pushed into a corner when you want to use that kind of stuff. All right, let's see if I can get one last second here. I'm going to need it. There's one more minute because it would be kind of sweet to kind of get this done. Let's see. I hope this is a small file. One sec. Sorry, everybody. I know I'm being greedy here with everybody's time. What do we got here? All right, please be small. Yeah, good. It's going to be small. Really well. Yeah. Okay. So you can do stuff like this where you're putting in like you're doing arithmetic in the selection. So product name, unit price time unit stack. That's the total value for the product. So you can do that kind of those kind of operations to kind of nice. Very very useful. Right. All right. So this is like giving us the total value in dollars, I suppose, of the quantity. All right. And then yeah, okay, order by. So the tau operator is done by ordering. So you can order by the value here. So what this will do is just give us the order of the value of all those products. So let's see here. So and then let's see order. Okay, and then this is kind of annoying because it's going from we don't have any of this bratwurst in stock apparently, but what we want is actually get the ones that are the highest value first. So we're going to have to go into the ordering. If you go away, and we're going to have to do it in descending order. Okay, and so that'll give us this. Okay, and so we have whatever that is. We have a lot of $4,488 of that stuff. Get rid of this. And then let's go beyond the product name. Okay, that then we get into like operator. So this is kind of like actually the way this is something where you probably want to like is very ancient SQL. There's a new regex. You probably want to use regex in this in likes instead. But this right here is excuse me. This is just showing that we can do this kind of partial matching. Let's just see if this gives us anything. Product name. Annoying. Undo. Sasquatch Ale, yeah, because it was ALE. All right. Yeah, so that's just okay. So that was just kind of like your kind of first kind of like quick introduction into SQL. We're gonna do a lot more with like grouping and group by and the aggregate operators like that in the next lecture, which won't be until next Monday because we have recitation on Thursday. All right. If I want to be done, right. Yeah, lab 1 and lab 3 are to be done alone. Lab 2 you can do it in groups of up to 2 people. Let's see, I got another question. The value is the same. They sorted by. When the value is the same, it's that arbitrary tie. It's the arbitrary tie. So it's that whole thing with the tau operator where it's just like it picks its way that it wants to. You don't really, you can't control that. For recitation, you lose points if your solution is incorrect. No. In fact, you get no. Sorry. Well, you get the same number of points. We like it when you're incorrect because that generates discussion. So please be incorrect. If everybody goes to recitation, everybody gives the correct answer. What kind of recitation is that? All right. So we really appreciate it when people get things wrong, but they have to try. Okay. I'm wondering about Lab 0. It says we should connect to the school network if we are working from home. Is there a particular reason for this? Does it really say that? I should go back and then change that because I prefer that everybody just does this on their own. That is that they install PostgreSQL completely on their own computer and not because that'll give you more practice installing software. Just in general, it's good to kind of to centralize things on your own, to take command of systems yourself and bring them onto your own hardware. That's a generally better thing to do because then you're isolated from other people. Okay, I mean you're isolated from problems that other people might cause. Let's put it that way. All right, so we don't have any of this. Okay. The value is the same.
Examples. Will the recitation be over Zoom? My recitation will be over Zoom. I believe, I'm afraid that the TAs are going to decide today if they're going to hold theirs over Zoom. We'll make an announcement about this. I think that because Omicron is really rampant, that they're going to probably do theirs over Zoom as well. And it sucks. I mean, it sucks, but it's the world we live in, at least for a little while longer. But I don't know. They haven't decided yet. Okay. How to show recitations over Zoom is somewhat difficult to explain. Oh yeah. Well, you got to have you got to do screen sharing, and you got to then, like, if we get called on, then we just kind of wait for you to kind of get your screen share set up, and then you basically speak over the, explain it kind of like I'm doing here with this SQL stuff, which you guys will be better than me. All right, it says so. Yeah. Oh yeah, screenshots of paperwork. Yeah, so the screenshots of paperwork. Yeah, absolutely, absolutely. Okay. All right, everybody. Well, I'm glad. I mean, we're caught up now. I mean, we got through all the SQL, all the really basic SQL, and I'll put up this recording here, this video for lecture today, and I'll also copy up these files. I'll try to fix them a little bit, but that won't come until later because I have to later on today, this afternoon. Okay. Alrighty, right, people. If there are any questions more, then just type them in the chat. Otherwise, I'll give you guys a minute here in a second. Otherwise, see you all on Thursday. Okay. And then I'm going to say end.